Well, welcome to a what will turn out to be a lengthier video than usual because I'm going to be demonstrating something and have you work right along with me. So I want to be sure you have everything you need to be prepared for this. What I'm going to be demonstrating here is how to do what we refer to as ray diagrams. This is described in lesson 3 of the tutorial. In particular, I'm focusing on the ray diagrams section, which is the fourth section in there, part D. And so in order to do this, I've set up a couple of templates for you in your workbook. So page S28 is actually a page on which you can do these drawings for practice. And then there's a reference page that kind of summarizes a lot of the key things in the tutorial. That's found on page S27. So those should be nearby each other in the workbook. And you're also going to need a straight edge. A clear ruler works really well for this. And 3 different colors of pencil or pen to make this diagram. So I'll let you maybe pause it here and go get those things, and then we'll get started. Now I'm going to be reviewing a lot of the things that you see in the tutorial, but also actually stepping right along with what he describes about how to make ray diagrams. By the time we're done, we're going to know how to do this and how to describe the image that you see when you look into a curved mirror. Now this particular tutorial is for a concave mirror. So if you look at page S28, I've got some templates set up that show a concave mirror. Now, if you have a spherical surface, there's, I guess you might call it the inside surface and the outside surface. We're looking at the inside surface. So if we imagine taking a piece of glass and silvering it on the inside of the sphere, then we have the concave side. Later we'll look at the convex side of it, which would be like the outside. You're probably more familiar with the convex mirrors because you'll find them on the side of a truck, maybe security mirrors in a convenience store, or busy intersections and hallways and things like that. So here's the concave mirror. I like to also think of it like as you look at it, it caves in the middle. That's a way of remembering concave. And just to point out some of the important features of this, I have drawn what is referred to as the principal axis. I usually abbreviate it PA. That's the axis that goes right through the center of curvature and the center of the mirror. Now the center of curvature would be, if we were to take the actual sphere that this mirror was cut from and find the center of that sphere, that's where it would be. So in this case, I've marked what's called the focal point. Now we're going to see that the focal point is an important point as well, but there's a relationship between the center of curvature and the focal point, and that relationship is that the focal point is halfway between the center of curvature and the mirror itself. I've got little grid lines here to help you count. So we just call each of these a centimeter. The focal point is 5 centimeters away from the mirror, which means that the center of curvature has to be an additional 5. So I'm just going to put a little mark right here, maybe a line, and then mark that as a C for center of curvature. On the tutorial, he'll always have his marked that way as well. Now, our goal here is to imagine that our eye is looking at the mirror. So I sometimes like to think of the eye as being far away, and I draw my eyes sometimes like this. So you're looking at the mirror, and of course you're also going to look at the object. But we're trying to figure out what is that image going to look like. There is an image that is formed by the light rays reflecting off of the mirror, and then the eye tries to pick up where those rays seem to be coming from. Do they all seem to be coming from the same point? And they do, and that's what we call the location of the image. So just like we do for plane mirrors or any other kind of mirror, if we can find that point where all the reflected rays seem to be coming from that hit our eyes, then we will know where the image is located. So the key here is the law of reflection. If you can imagine maybe playing basketball on a curved backboard, or playing pool where instead of a straight pool table you have a curved rail, or anything like that where you're throwing something against a curved surface, we'll get all kinds of strange reflections off of there. But the one thing we can be sure of is that they will all obey the law of reflection. So whatever angle the incident ray makes, that's the ray that's approaching the mirror, will reflect off of the mirror at the exact same angle on the other side of the normal line. Now, we're not going to draw a bunch of normal lines here because some really smart geometry people way back long ago figured out some shortcuts for us to use. And in the tutorial, he describes 2 of them. And on my page, S27, I describe even a couple more than that. So I'm going to use 3 of these shortcuts to show you how quick it is to find the image location. So if you take one of the colors that you have, we're going to draw one of the light rays that might come off of this arrow. Now, we're going to use an arrow object just because it's so easy to draw. I mean, even easier than stick figures. So imagine all the different rays that could come off of this arrowhead. We'll just focus on the arrowhead at first. Some would be going, up and rightward and up and to the right, down and to the left. So we just want to take one of these that might happen to be going directly parallel to the principal axis. So the way I've got it laid out is it should be right along one of those grid lines. So always draw a little incident ray heading towards the mirror with a little arrow going like that. There's going to be a lot of little arrows like this. You've got to keep straight what's what. That is representing a light ray that is heading towards the mirror. Now think of it like a tennis ball that you would maybe throw at a curved wall like that. And try to picture how that tennis ball would reflect off of there. I hope you can kind of imagine that this would come downward a little bit and head back leftward. Well, the actual angle that's made is what we describe in rule number 1, which says incident rays parallel to the principal axis will reflect through the focal point. I'm just reading from page S27, and I'm ignoring the part in parentheses because they only apply to the other kind of mirror. Incident rays parallel to the principal axis, which is the one that I drew there, will reflect through the focal point. So you can put your straight edge back down and come right off of the mirror the way I have it drawn here and right through that focal point. Draw it just like that. Now that's a reflected ray, so I show a little arrow going away from the mirror. And there is the ray for rule number 1. So one thing I can be sure of is now it doesn't look like that ray is ever going to hit my eye, but remember I've just drawn one eyeball there. It's quite possible that there's somebody else looking down here. And one of the keys in the tutorial is that it doesn't matter whose eyeball is looking at the mirror. Everybody's going to be seeing the same image. So along that line lies our image. We're going to draw a second ray to see if we can locate where exactly on that line that is. And I'm going to read rule number 2 off of page 27. Incident rays that go through the focal point. That means incident rays that's on the way to the mirror. If it goes through the focal point, then it will reflect back parallel to the principal axis. So there's a section on the focal point in the tutorial that describes this. So we grab a different color and draw an incident ray that, as it heads towards the mirror, goes through that point labeled F, and that is the one that will reflect back parallel to the principal axis. Now use the grid lines there to kind of guide you so you get it pretty straight. We have something like that. Now here we might imagine somebody else's eye that happens to be located there and might actually see that reflected ray. And here's a rule that is not described in the tutorial, but I think is very helpful. It is described at some location, but it's just not in this section. And that is, there's a point here right in the middle of the mirror. It's referred to as the vertex. And if a ray happens to hit right at that location there, so grab a third color, there's the incident ray heading from our object to the mirror. Notice that that is exactly in the center of the mirror. And so we actually have a normal line. That principal axis does form the normal line. A normal line goes perpendicular to the surface at each point. And we're getting a little bit advanced here in geometry to talk about a normal line to a curved surface. But you can trust me that that dashed line there, the principal axis, is also a normal line at that point. So what does this mean? Well, it means that if we could figure out what the same angle is on the other side of the normal line, then we'll have our reflection. So we're just going to draw a symmetrical line to the green one that I drew there. I'm not sure if it shows up very well in green, but the way I'm going to do this is, if it's symmetrical, then by the time it gets back here to the same distance from the mirror as the object was, it should be the same number of squares below as the arrowhead is above the principal axis. So watch this here. I'm going to count the height. 1, 2, 3, 4, 5, 6, 7 squares high is how tall this arrow is. So that means 7 squares below 1, 2, 3, 4, 5, 6, 7. Right there is the location where a symmetrical line should go through. So I'm just using a little bit of geometry rules here. It's probably been a while since you've seen geometry like this. But it's easier than taking a protractor and doing what I'm going to show here. That angle, we call that the angle of incidence, and this angle here, the angle of reflection, must be equal to each other. That's the law of reflection. But what I'm using is the fact that a triangle formed with those angles, the right triangle here, must be identical to a right triangle symmetrically below the principal axis. Okay, so I found the special point that I was looking for originally. This intersection point, notice all of the reflected rays that would ever hit anyone's eye, whether those eyes are over here or down here, and I could certainly draw a whole bunch more of these, but I just don't have shortcuts for them. All of those rays that hit these eyes seem to be coming from this special point there, and that is the image of the arrowhead. So I'm going to know that my arrowhead is there. Now I just need to find the rest of the arrow to figure out what the image looks like. Now this is also described in the tutorial, and he actually shows the process of applying these rules to the rest of the arrow, but I'm just going to take the shortcut, and he also describes it too, that if we start with a perfectly vertical object, we can be sure we're going to get a perfectly vertical image. And any object that is on the principal axis will also have its image on the principal axis. So that means the tail of the arrow right down here is also on the principal axis. And if this arrow's image is to be vertical, it must be directly above where that dot is that we found before. So here I'm pointing to the tail for the image, and here I'm pointing to the head of the image. So I'm going to put in the rest of the image. So now I can tell which way everything points and how big everything is, and that is the location of the image. Now I always like to describe the image with 4 different criteria, and this is described in the tutorial. The first question is, and this is the easiest one, is our image upright or inverted compared to the original object? That means, is it in the same orientation or has it been flipped over? And I think it's easy to see here that because our image is pointed down instead of up, that we have an inverted image. So that's one description of it. The second would be, is it real or is it virtual? Now, if you don't remember the difference between those two, it's a very important thing to review. Real means that these reflected rays off of the mirror, the ones coming off of the mirror now, really do intersect somewhere. It's not just apparently or virtually intersecting the way we saw with the plane mirrors, and we will also see with some other mirrors. So the fact that they really intersect makes this a real image. The third criteria is the size of the image. In this case, we have an object that is beyond the center of curvature, and that is going to give us a smaller image. And we have some math equations that we'll use to figure out just exactly how much smaller. And the location of the image. How far from the mirror is it? This one is between the center of curvature C and the focal point F. And that's one of the hallmarks of any object that we have at a location that starts beyond the center of curvature. So anything back here that I'm indicating, if you put an object there, we will get an object somewhere within this boundary here between C and F. So there's a look at how we draw a ray diagram to find the image in a concave mirror. And in this case, our object was located beyond the center of curvature. Now I'm going to stop this one, and there's another segment that's going to show what happens when we have the object closer than the focal point, because things end up a little different there. But we'll do that separately. We'll practice this during class, and this is all described and actually animated on the tutorial. Make sure you're not skipping those parts that say animation, because it shows the process of how these rays reflect off of mirrors and how we can find the location of the image from those. So if you have more questions, of course, you always can see me in the classroom.